Hi, everybody. Good afternoon. And I hope you're enjoying this lovely day at the moment. But thank you for taking the time to join us in our webinar series today, which is on a career in fusion energy. So thank you very much for joining us this afternoon for that. So just before we get kicked off, just some few housekeeping, professional development. So obviously, if, as a member, and especially those as graduate members, it's really important that you do log your CPD hours, as you have to make up about 35 hours a week, a year. So you can do so on your membership dashboard, just there, clicking in My CPD, and you can log this as 1 hour of CPD. In addition, those who are due to graduate, who have just finished, I guess this year in 2022, you have the ability to transfer to become a full member for free. And again, you can do that through your membership dashboard, where you'll see there you can become a full member. And this is available to all those who are currently graduating, I guess this autumn. But you can get started on becoming a full member and join our graduate membership rate. So there's 3 easy steps to get graduate membership. So as I said there, log in and choose transfer to full membership on your membership dashboard, and then you'll be prompted to confirm all your details. And then soon after, you'll be emailed to request transfers and to verify your qualifications. So, and again, you can check on our website on the different ways that you can verify your qualifications, which is pretty easy to do. And then this will be sent to our membership and qualification board, which meets once a month. And then from there, they'll do all the checks so that then soon after you can be able to apply the post-nominal MEI, member of the Institute of Engineers Ireland, to your LinkedIn, to your profile, and anything else, and start making a saving of over €700 with our graduate membership rate. So again, these are all 3 easy steps, and I do encourage you, if you're not already done so, to do so soon after this webinar. If there's any questions at all relating to transferring to graduate membership or anything related to Engineers Ireland, you can contact us on our phone, by email, on our website, but also make sure you check out our LinkedIn, Instagram, and Twitter for any more information about graduate membership also. But today's webinar is now going to be presented by Keelan Keogh, one of my colleagues from Engineers Ireland. He's going to speak about his career in fusion energy. He's a chartered mechanical engineer as well as policy officer for Engineers Ireland. Graduated in 2012 with BA in manufacturing and design engineering from DIT Bolton Street, now known as TU Dublin. And he's worked at UK Atomic Energy Authority Fusion Research Lab over 9 years. So now, thank you very much, Keelan, for joining us, and I'll pass it over to you now to give your presentation. So thank you.
Okay, so yeah, thanks, Pierre. Yeah, as Pierre said, my name is Keelan Keogh. I'm a chartered mechanical engineer. I'm now the policy officer for Engineers Ireland, but before that, I did work in fusion research, developing robotic maintenance systems mostly. So that was a research program working with Europe and based in the UK. So I was just going to do a presentation sort of highlighting fusion research and a little bit about me framed around my career going through that. So hopefully you'll learn how a fusion reactor works and also about maintenance of them. So that should be interesting. So first about me. So yeah, I was in DIT in 2007, 2012. They took a photo of me my first day, first year, after I got hair dye cut out of my hair, so I had very short hair. And then that photo stuck with me for the entire 5 years I was there. I was the president of the DIT Circus and Juggling Society and organised Dublin Circus Festival. And I also got the opportunity to work for my final year project with ESA and other European space agencies with the DIT Space Research Group, where I designed a hatch mechanism for a novel telescopic boom. And it was really this sort of research work where it was developing technology for a bespoke purpose that I sort of really enjoyed. Application of engineering where you're not so much focused on efficiencies, you're really focused on trying to achieve a task and get that done. So as long as it's good enough, it's good enough and has to work. So with that, I then moved on to the UK after graduating, and I worked at Culham Science Centre. I was there for 9 years. So Culham Science Centre is just outside of Oxford, about 10 miles south. So it's a very nice cycle down the river from Oxford. And this facility is focused on development of fusion energy and houses two quite significant experimental reactors. There's the MAST reactor and the JET reactor, which is a European project. It's based on an old Air Force base, so that's why it's got these long straight roads. The reason they're really focused on this is sort of over the last 100 years or so, humanity's done a very, very good job of sort of keeping the darkness away. And we've managed to develop a lot of interesting technologies and increase our energy use. And you can see quite clearly at nighttime in the world how much energy is used and how much lights are on. In the next sort of by the mid sort of point of this century, that is expected to increase drastically, particularly in more developing countries as they increase their energy demand. This is particularly noticeable in sort of South Asia, where it's expected to increase pretty drastically. This graph is quite useful because you can see on the inner graph, the world population is expected to go up by the end of the century to around about 9 billion people to 12, somewhere around that figure. And the major graph here, it shows the energy uses, the energy production kind of in that's expected from that. So there's three scenarios. A being if technology didn't develop and we just kept using our energy as the population increased. B is based around sort of technology efficiencies developing, which is likely, so that's the most likely scenario. And C is what we're really looking for, which is increases in efficiencies and also reduction of CO2 production from our energy production system. So this is a lot of renewables and other systems. And one of those other systems that could solve all of world's energy problems is fusion. So fusion is the power source that warms the sun. The sun is significant. You can see it's a nice sunny day today, so we're all familiar with the sun. It is big. It is about 99% of all of the mass in our solar system. You could fit about 1 million Earths inside of it, and it generates quite a lot of energy every day. It's got a surface temperature of around about 5,000 degrees and a core temperature of around about 15 million. It's made up mostly of gas, hydrogen gas, and the majority then is a plasma, but the hydrogen gas sort of floats around with electrons orbiting a single proton. And then the plasma is more of a particle soup. So this is where your electrons and your protons are stripped away from each other and they're just moving around, moved by gravitational forces of the sheer volume and mass of the star. And what's interesting here is because you've got protons, they are positively charged, so they will constantly try to push away from each other due to the electromagnetic forces. But when you get close enough, the strong nuclear force takes effect, and that pulls them together, creating a fusion. So why fusion? So in this sort of case here, I've got two atoms from isotopes of hydrogen, so deuterium and tritium. When they get close enough to fuse, the strong nuclear force pulls them together. They fuse completely and generate a helium nuclei and an extra neutron. And the extra neutron is accelerated away from the interaction at very, very high speeds. Why that is interesting and is all thanks to this little guy, Albert Einstein, and his equation that everyone probably knows, which is E equals mc squared, or in this case, I've got E equals the delta mc squared. So E is energy, the difference, the delta of the mass times the speed of light squared. And if we go back to our deuterium and tritium, we have our deuterium and tritium weigh slightly more. If we put this on a little tiny weighing scales, our deuterium and tritium would weigh slightly more than the overall mass of a helium and a neutron. So because there's now a difference in mass, that mass has had to be converted entirely into energy. So that is, in this scenario, this sort of scale, we've converted physical matter directly into energy. So matter and energy start becoming interchangeable, which is quite an odd sort of thing to perceive. So beyond general engineering and really down in high-end physics. So that's how fusion works. Now everyone's an expert. Stepping back to plasma. So plasma is the fourth state of matter. And the difference between our matter is just general amount of heat that you add. So solid is the sort of normal one that everyone is really familiar with, where your atoms are all lined up in a logical structure, all connected. Liquid, they're still connected, but they're more fluid now, so they don't spread out, but they stick together, but flow around and fill gaps. And a gas, they are moving away from each other and trying to fill all available volume that they're in. And then after that, you end up in a plasma, where it's this particle soup that I mentioned, where your atoms are stripped down to their component parts. So your nuclei and your electrons are just free flowing, moving around in random directions. So if you put them inside of a tube, they would just be moving around. It'd be a very hot tube, and your particles are just moving around in there. But as I said, because they have a positive and negative charge, we can do something interesting with this. So without a magnetic field, they're just moving around. But if you add a magnetic field, we can now manipulate and control them. So they will start to orbit around the magnetic field lines of the magnetic field. So with that, we're able to then do something with plasma. We can contain it, we can control it, and we can manipulate its position and so press it together or let it spread apart. And that is exactly the concept and development that they've taken to develop a certain type of fusion reactor. So if you get your cylinder with a magnetic field and you bring it around to the other side, you can then create a donut shape or a torus if you're into maths. So this torus shape is the basic of a tokamak. So you've got a donut-shaped plasma that is contained inside magnetic fields, which are called toroidal and poloidal magnets. And these are able to bend and control the plasma and position it inside of the center and bring it closer together. As I said, that is exactly the basis of JET. So JET is the Joint European Torus, or Joint European Tokamak. So this is a tokamak design. It was built in 1983. It's the world's largest tokamak. It's got a major radius of around about 3 meters and a volume of about 100 meters cubed. And as I mentioned, the sun has a core temperature around about 15 million degrees. And the sun is massive. It's 1 million times bigger than the Earth. So if we wanted to create fusion on Earth to increase our likelihood of our nuclei getting close enough together for the strong nuclear force to increase, we have to increase their energy so that they're interacting more often. So instead of being 15 million, the temperature inside a jet reaches around about 150 to 200 million degrees, which is the hottest position in the universe that we know of. It's also got a really ridiculous high temperature delta. So within about 1.5 meters, there are super cooled components in the cryostat, which are down at nearly absolute zero. JET, it has several world records. It's the largest fusion reactor, and it also has held, this year it broke its sort of previous records about energy production. So generated 21 megajoules of energy for a consistent 5 seconds, which absolutely destroyed its previous records. Still generating less energy out than it's putting in, but it is on the right track, and that's just because of its size. It's not big enough. So you can see here in the image JET, there's a scale person. This is sort of one of the original images of JET, and there's these large orange limbs around the outside, which are like like a transistor for a system called ohmic heating. And then what JET looks like now is, after 40 years of operation, is this sort of mess of wires and scaffolding and experiments all strapped to the side of the vessel inside of a very large room called a torus hall. So the torus hall is roughly about an acre sort of size room, and it's about the same height as it is wide. So 1 acre cubed is the size of the hall that the machine sits in. It's a very impressive machine, but it is getting quite old now with its equipment. So there's a plan for future machines. So the next machine after JET is ITER, which I'll talk about a bit more in detail in a second. And then after that, we have a demonstration reactor. So JET is an experimental reactor developing fusion. It was designed to try to break Q1, which is energy in equals energy out. And ITER is designed to break Q10, and it's done that from the lessons learned from JET. And then it's still an experimental reactor. And then the demonstration reactor after that would be the first reactor that generates fusion energy and then puts that onto a national grid. And lots of individual groups are developing their own demonstration reactor. So there's a European demonstration reactor, there's a UK one, there's an American one, Chinese, South Korean, etc. There's all these unique designs that are all being developed based off the lessons learned from ITER and JET. And sort of timeframes, conceptual studies are being developed now, developing key technologies and going into a design phase for the reactor. And then by 2030, we'll go into a build phase and then should be operating 2040, 2050. Various groups say they can do it faster or slower, but that's a rough timescale. ITER is big. So here you've got a model of ITER next to the model of JET. You can just about see down here in the bottom corner, there's a small person and a small person over here for JET. ITER is about 10 times larger in every proportion. And it is quite colossal. The vacuum vessel is sort of cathedral sizes. If you were to stand at the bottom of it, it's about 10 meters straight up to the roof. It's organized in a way as an international project and representing about 80% of the world's population, who all have a vested interest in energy development. So it's funded by China, Europe, Russia, Japan, South Korea, and India. And part of the funding is physical funding, sending the money and people directly to the south of France. And a large portion of it as well is also developing technologies in these individual groups, which are then sending the equipment to South France for full assembly. And once we've built ITER and developed that, then we can go on to a demonstration reactor. And this is where our demonstration reactor is a small green component in the center of this image. And it's a very small component then, and you've got your power supplies, maintenance systems, turbine halls, and everything else all building up around that. So your fusion reactor is a very small component, and you use your fusion reactor to transmit the heat through what are called blankets, which then have a heat exchanger, converting it into a steam boiler, making boiling water, and then going into a Victorian steam engine and making electricity. So it's quite, I always think this is quite fun. We've spent nearly 100 years development time, and you've created the power of a sun, able to control it, manage it, and then you hand all that over and use a piece of Victorian technology to generate some electricity. Another area, and that is the remote maintenance work. So this is the work that I particularly did. So this is the maintenance side of JET. So we use a system called Mascot. So in the early stages of JET, it was all done by people inside of the vessel wearing various types of suits to keep the machine clean and to keep them safe. And then in the early 2000s, we started using the robotic system called Mascot. Mascot is mounted on a telescope, on a boom arm, which is sort of 12 meters long. It's articulated so that it's able to follow the curvature of the vacuum vessel as it goes inside. And there's a second one as well, which has a task module on the end. So this is sort of a chest of drawers that holds all the tools. So you've got Mascot and task module, which, yeah, chest of drawers. Sort of the early tooling was more focused. It was remote, but it was a lot more appropriate to be used by a human hand. So there was a few challenges with operating it with Mascot. And then modern tooling gets a much better photo shoot with better lighting, but it's also got a lot more, all the components are specifically purpose-built, designed for operation with Mascot, based off first principles. So this is where a lot of this work goes. So there's hundreds of tools, all developed and all stored for various bespoke tasks, all developed. And early planning is done in sort of these old systems, and we did test running and the world was black and white, so clearly not as good as it is now. And then in 2011, this is the sort of operations that we were doing. They were doing, I don't work anymore. So this was replacing all of the first wall components inside of the vessel. So all these tiles, and the operator sitting under the controller here is able to feel exactly that through a bilateral control system. So you can feel the bolts tightening and the screws engaging. When JET is in operation, the maintenance teams are doing planning for the next shutdown. So they are planning this out in VR modeling. So you're able to rehearse every single movement and plan out exactly everything that's going on. And it's just an image of how Mascot enters the vessel, sort of comes in a Superman pose and then rotates around, and then the arm is able to feed all the way in. So yes, so remote handling is done mostly with Mascot, which is sort of the main workhorse that we work with. It's controlled by a person sitting underneath the manipulator controller, which is a one-to-one scale system. So as you move the arms here, you can feel the arms move inside the vessel. They're about 100 meters away, just over. And this is a full bilateral control system that allows full feedback of the mechanism. It's quite an interesting mechanism because if you're sitting in the controller seat, you can almost hear stuff happening inside of the vessel, because anything that the arms pick up from their interaction will then reverberate back through the arms and linkages above your head. And it's all positioned in place with VR modeling. So there's a full feedback loop between the VR and the real world. This is a good VR image of Mascot coming in vessel and sort of illustrates how it works. So we've got around about 30,000 hours of operational experience inside of the vessel through 8 different shutdowns. the biggest one being 18 months, where all 7,000 components were changed inside of the vessel. So every single tile was taken off and replaced with one that is more like what they're building for ITER. So in that, they've done every kind of operation that you would expect with a person. So it's a very versatile system. So they've done handling, cutting, welding, grinding, dust collection. They've got a sort of Hoover that's not too dissimilar from a Dyson, but legally not a Dyson. As I mentioned, Mascot has 2 fingers, and original tooling wasn't designed perfectly for that, but now everything is designed around these interface blocks. So all components have these small interface blocks, and everything is planned to interact with them. There's been over 20 years experience in developing the technology and the skills here. So early stages, sort of one person sitting in front of a couple of screens and operating the equipment, sitting on a dodgy little chair. And then nowadays it's a much more moody lighting area with better screens. I think there's about 18 screens in the room. And you've got your Mascot operator sitting underneath the controller. An engineer in charge who has a full sequence of absolutely every move, every planned sequence, and everything is meticulously detailed before we go into vessel. And then there's the boom operator who drives the manipulator boom. So other work that goes on at Culham site is research and development. So for demo, so I worked on this. One of the things I did build was a full-scale image of a demo blanket. So these are the first wall components that are inside the vessel that require removal in the maintenance activities. And for a scale, that there's one there in the hull. It's roughly the size and weight of a lorry, but held vertically, and is then lifted out of the vessel that way. And it has to be positioned within 20 millimeters. So you've got something the size of a lorry parked next to something else the size of a lorry that you've positioned vertically with a 20 mil gap between them. I did a lot of research and development on laser processing and optics trials, so developing cutting and welding to be used inside of demo, because there's not a lot that you can say specifically about future reactors because they're not designed fully yet, but you can definitely say there will be pipes. So developed a lot of the cutting and welding processes for these pipes with a small test rig like this, cutting through DN90 pipe, so a 90 millimeter diameter pipe, which had a 5 mil wall thickness made out of stainless steel. Here's a video of a welding tool inside of the pipe. Takes about 30 seconds to weld through this 5 millimeters of steel. If anyone knows anything about welding, sparks are bad, so this looks pretty, and that's why I used the video, but it is not a particularly great weld, but this is one of the early stage welds. So through that technology development, then we built this sort of Torpedo Fellow, which was able to go down a longer pipe and was able to clamp onto the inside of the pipe and pull it together with pneumatics. And it was able to cut and weld in the 34 seconds. So I was able to cut through 5 millimeters of steel, and we were able to weld through it as well. And as you can see in these sort of images below, the welds were quite good. There was no porosity or anything inside them. This is done with a X-ray tomography in the lower right. So that's a full X-ray image, like an MRI scan of inside of the weld, so you can't see any inclusions in that. RACE and UKAA do a lot of other work, so they do standardized testing. So this is standardized testing that was developed in America, and at Culham, there's the only European version of these tests. So there's ones for autonomous flying vehicles in a machine called the area called the Avery, and then there's a ground-based one as well that has these sort of blocks of wood and some robot driving around in them there. The they also have access to a few spots from Boston Dynamics, and they tested that there as well, and it hilariously just walked right through the test. Compared to some of the other robots that do struggle, it just achieved all of them without any great difficulty. There's also a machine called Tarm, which is a very large robot. So this is used for developing, for the future reactors I mentioned, their scale is significant. So when you end up at that scale, you've got deflections of your robotic system, and shaking and vibrations all have to be considered in the design and how it's all managed. So Tarm is a test bed for that, where you're able to move it and position it and feel and compensate for the movements. So it's got a long arm on the end with a mascot that mounts onto the end of that, or a different manipulator. And then that's able to perform various tasks and operations inside of the work hall. There's also a lot of work with autonomous vehicles going on in Culham. So Culham, as mentioned, used to be an old Air Force base. It's got around about 10 kilometers of roads with roundabouts and big roundabouts, little roundabouts, crossroads, junctions, bunch of physicists and scientists who are not really paying attention and are relatively expendable. So it's a good test bed to see how these autonomous vehicles drive around and interact with all that. So they've developed there, and then they move into real world applications in Oxford and further afield. And yeah, so collaboration really is key for sort of the operation and development work at Infusion and at Race and Culham. So it does a lot of work with other universities around the world and around Europe mostly. So there's a lot of opportunities for development there, and there's PhDs and stuff like that that are always going on. With Brexit and everything else, Ireland is still in a good position where we can go across and work in the UK with relative ease compared to some of the other European countries. And fusion research is still part of Euratom, which is a Europe-wide structure rather than being connected to Brexit, so it's self-funded. So that is everything. So